So remember, join us on the Slack and ask questions and keep the discuss going in using the channel built as data science project. So today we have a special guest, a speaker of today is Bisi Josh-Falade. Is a researcher, student, and digital product professional with over 50 years of experience. She combines her extensive expertise with data science and machine learning to create innovative product and solutions. She's also an active product volunteer at WWCode Data Science, empowering and uplifting the community. She participates in conferences, forums, and panels, contributing to discuss on products development, innovation, technology, parenting, and lifestyle. In her free time, Bisi grooms her passion for digital designs and virtual reality. So yeah, very happy to be with you, Bisi. Well, the stage is yours.
Thank you so much, Victoria. Hi, everybody, and welcome to the fourth session of our of the series. So just give me a minute to pull up my screen, and we then take it up from there. Okay. Please confirm that you can see my screen.
Yes.
Yep. Okay. Okay. Great. Thank you. So just a quick reminder that if you have questions, please put them in the Q&A box, and they will be attended to as we progress. Also note that the notebooks and the recordings of the session would also be available on our YouTube channel. So quickly today, we're looking and we're focusing on baseline models. And this is a quick run through of our agenda today. We'll be looking into machine learning, an overview of what machine learning is. I know that we all would have at one time or the other heard what machine learning is, but this is just a reminder, or like a quick reminder on what it is, and then also a quick look at the major categories or the major classes of machine learning, and the differences, what they are, and what differentiates them. Also, we'll be looking a bit at the difference between regression and classification, two major machine learning tasks that are being used and being done across industries. We also look at differences between machine learning, deep learning, and artificial intelligence. And then we go quickly into baseline models. What exactly are they? What's the importance of having a baseline model? Why should we really consider having these baseline models? And then we'll go into our collab notebook to proceed with our work today. So a quick background on what machine learning is. A lot of people, it's more like a buzzword to a lot of people at this moment. Machine learning, artificial intelligence, data science, and a couple of these words are kind of flying everywhere, and people get lost in terms of what exactly it is. But machine learning is typically a branch of artificial intelligence. It's a subset or from artificial intelligence, and it's basically it involves data and learning from existing data to probably make predictions, or to make certain inferences about future things or future occurrences. So it's more of building from a data, with a data set available, building and training a model on a data set and using that same model that's been built to make predictions on new data or unseen data that is available. And there are basically three categories and three categories of machine learning, or three types of machine learning. We have the supervised, we have the unsupervised, and we have reinforcement learning. um, so usually supervised, like the word implies, supervised means you have a data set and you have corresponding labels to to that data set, and you want to make predictions on that set of data. Because once you have the data set and you have the labels as well, which are usually what you intend to um, make predictions about, you can create a model that is trained on that data set and then can use that to make predictions on new data that will be um, exposed to that model. And then we have the unsupervised model, which involves, a data set, but um, the 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 labels are not available. Labels in terms of the features or specific things that want to be that you would like to maybe um, make predictions about are not available. All you have is just a data set, and you don't have corresponding labels to that. So what supervised, unsupervised learning works on that data, creates a model from that data, and then can use that same data to make predictions on future data that will be exposed to it as well. While we have the reinforcement learning, which is typically learning from the environment and then being reinforced, just like you would usually train an animal or a domestic animal, like a dog, or to make decisions, and then you reinforce when good decisions are made. More like you give a thumbs up, or you give a reward for making accurate decisions. And when wrong decisions are made, you also give penalties or reprimands. So reinforcement learning works on feedback and rewards. And then in terms of application, machine learning has been used, and is being used in various fields. We have the finance, retail, transportation, real estate, medicine, healthcare. It's been used out there, even in education, in law, in the legal terms, in the legal field. It's being used across board, and it's growing in importance because we have data everywhere. We have data that are around us, and at every point in time, we have huge, huge, gigabytes, huge terabytes of data being generated, and um, increasingly it's growing in importance, and it helps eventually to increase um, productivity, accuracy, and then decision making. So this is just a table, explaining these differences. Is basically exactly as I've shared, presented in a tabular format. You know, what supervised learning is, unsupervised, and then reinforcement learning. Um, the fact that supervised learning involves label data, unsupervised, we do not have unlabeled data. Then for reinforcement learning, no predefined data. And then the training, where you have also the approach in terms of the machine learning task. Then in terms of regression and classification, so these are two common machine learning tasks that we would that are usually carried out in solving problems, or even in in all data tasks. So regression basically involves predicting a continuous quantity, what trying to predict a continuous value of a certain feature, trying to predict a quantity, what value, trying to pin a value to a certain, for instance, predicting predicting the number of cars that will be, probably imported into a country in the next couple of years. It's you're trying to predict a particular value, and in that case, you would be using a regression model in that case. So that would require, you coming up with a regression model and then using that to make the prediction. And for classification is a bit different. It's majorly um, involves predicting a discrete label class. So where you would have data that are labeled into two or more classes. So where two or more classes are created, there is a data set, and then different classes are, you know are identified or recognized from the data set. So what typically would happen is prediction in this case will then mean, whatever data that is provided to the model, you know would then be classified into any of the identified classifications, that the model has eventually identified. So in this case, it's not a specific value, but then you're trying to put you're trying to fit a certain data or a certain element into one of the categories that has been identified in in as part of the data set. So it involves, a classification program usually involves two classes. It could be two, you could have two or more classes. Where there are two, it's called a binary classification problem. Where you have more than two classes, it's called a multi-class classification problem. An example is email classification. So having said that, it's again important to look at what the similarities and the correlation or the relationship between machine learning, deep learning, artificial intelligence, and all those buzzwords that are flying out there. What exactly, um, how do they relate? What's the relationship between them? And artificial intelligence, like is a broad, um, that's like the superset. It involves using machines and using systems to do typically what humans will do, in terms of reasoning, in terms of decision making, in terms of thoughts and reasoning and ideas. Typically developing machines and computing systems that do exactly what um, ex- that will do exactly what humans, will do. And like I said, it's the superset. It's all encompassing. It's the big basket, if I may use that word. And it's usually designed to operate automations. They are used for automations for when environments are changing. They used to make decisions based on whether and on certain environments, incomplete information. And they are usually used for in that areas. And basically they're used in areas, they're they're usually, they involve areas where um things could be done better, could be automated. And maybe also precision is required, accuracy is required. Those are the things that fall under artificial intelligence. Because once systems are built to learn and to take the right decisions, they can then fit in and play the role of humans, you know um in that space. And then machine learning and deep learning, fall under artificial intelligence. They are subsets of artificial intelligence. Machine learning is, involves building algorithms that learn from data. So build algorithms, build models that learn from existing data, and from there, the models can actually make decisions based on what has been learned, or the knowledge and the information that has been learned from the data set. And from the previous slides, we see that machine learning is basically three categories: supervised, unsupervised, and reinforcement learning. And then it's used in robotics, it's used in prediction, it's used in market segmentation, it's used in email classification, in prediction, in predictions, in analysis. It's widely used. And then deep learning um, is also encapsulated in machine learning. So machine learning, artificial intelligence is the big picture, is the big superset, and then we have machine learning in artificial intelligence. And now under machine learning, we also have what we call deep learning. So deep learning falls under machine learning. It's one of the areas of 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 significance under machine learning. So it's a subset of machine learning, and it involves building deep neural networks, that help to recognize patterns in data. So neural networks and complex networks that function similar to the mind, to the human mind, so as to recognize patterns in data, and then we make informed decisions based on the patterns that have been learned, and then helps identify features, patterns, allowing them to achieve higher levels of accuracy and performance than traditional machine learning algorithms. So deep learning is and has been applied in various areas. We have image, speech recognition, just to mention a few of the areas that deep learning has been used. Deep learning has also been used in neuroscience. It's been used to in building the neural network of the human mind, so building something similar to the human mind, and being able to make decisions, recognize patterns, and make decisions from them as well. So quickly, what's a baseline model? A baseline is actually a must for any machine learning task. So as we have explained in previous sessions, and also in previous slide, that um, in machine learning, the idea is to learn from existing data, and to learn from existing data, there has to be there has to be some a basis for comparison. So when that basis is formed, then one can then make build models that would then be compared with that baseline, and then one can make informed decisions. So just the same way we have what we call in the in the industry, globally, we have what we call best practice. Best practice is like that's the most important, not the most important, that's like a basis, like a foundation. It's like a level where a, I would say it's like a foundational threshold. Like you can't you it's something that you should as a necessity always do, and then you can build on it. So a baseline model, it's a starting point for comparison. You would really use a baseline model to compare what models have been built and the performance of the model that has been built against that baseline, and then it then helps to make decisions, probably to improve the improve the performance of the model that's been built, or to work on certain areas to ensure that the model performs optimally um, in this scenario, or in the task that it has been built for. So a baseline model is a must, and it's what we must always ensure that we, have, or we build into our machine learning tasks. So it represents the minimum level of performance that can be achieved without complexity, without any fine tuning at all. And we'll be looking into the importance. So the importance is first to determine consistency and reliability, of trained models. So when we're building our models, um, a lot of data and a lot of computation goes on, but then baseline models serve as, a platform. It serves as the minimum level and helps us determine the consistency of that model that's been built. So when we have a model that's been built, we can check if it's consistent, if it's in comparison with that baseline model. Is it consistent? Is it has it improved um, in comparison with the baseline, as the new model that has been built reliable compared to the baseline model? Does it work better? Does it perform better? Is it does it need to be modified to serve the purpose? So the baseline models are pretty much important because they serve as a benchmark um, to compare the actual model that is built and iterate quickly, if necessary. So we have the different models. We have some baseline regression models. We have baseline classification models, and we'll be looking into creating a baseline model as we go into our coding section. And then just to quickly mention again that we have a channel on Slack where you can ask questions and you can keep the discussion going. If you have questions, here, you can put them in the Q&A box, or you can also send them on this channel, and we would give you an answer as soon as possible. Um, so it's time for us to do our hands-on. If you're ready, please give me I would like to see a an emoji in the chat box. Okay, great. We're ready. Okay, so a quick confirmation. Let me know please if you can see my screen, if it's visible, if the notebook is visible, so I can move on.
Looks good here.
Okay, great. Thank you. Okay, so here is our notebook, and we'll go into the um, details the of building a baseline model. So again, from the previous session, we had our data wrangling and data cleaning, exploratory analysis done, and here we'll be going into building the model, based on the clean data. Again, our objective, in this machine learning task, is to actually predict a target value, um, whether it's a like or a no like. So we have a database um, of of songs, and then we have users who have liked. We have a target column, which is a like or no like for each of the songs. So our objective is to predict, whether a user would like a song or not based on certain features of that song. So the first thing is to have this notebook be connected and then import the libraries and packages that are needed. We have pandas, scikit-learn, matplotlib, and seaborn. We have a whole lot of this libraries that we're importing here into this notebook, and we'll just run that quickly to, and then here we have the clean data. We have to load the clean data. So in previous sessions where we had the data cleaned up, in this case, we then need to, we're working with that clean data because, that's what we need. That's the data set we'll be working with in this notebook. So we're loading the clean data. That's my drive that has been mounted. And then I have the file. This shows the data set. We have the different different features of each song, all in there. And then we have the target column, which is in here. 1 indicates a like and 0 indicates no like or dislike. So it's clean. It's super clean. It's been cleared out in the previous session. So the next step after checking this in for importing is to once again just check out the target values. That's the target column. What's the count? How many likes do we see? How many on dislike? So here we see that there is we have more likes than the likes. So you can actually use this to check if there is a balance between the target values or the target columns, or huge imbalance, because when you have huge imbalance, it can actually mislead the model that will be trained. And so in that case, there has to be some work to be done on the data. So once you've done that and we have just checked, there appears to be some good balance in there, then we do a split. So typically for machine learning tasks, you would train a data, you would train a model. So when you're for every machine learning task where you have a data set, it's best, it's advisable to actually split the data set into two, at the minimum two, training and testing. So when you train the model on a particular portion of the data set and then test that model that has been built. Remember that the model will recognize patterns in the training data set and then use the pattern that has been recognized to test the test data set. Now that test portion is again just to validate what the model is doing and validate the output of the model. So here we used the train test split function here, and we have our test size split into 30%. So here we're saying that we need 30% of the data set that we have loaded into this notebook should be set aside for test, and then the remaining 70% would usually be used for training. So the model would train based on the 70%, and then we have the 30% left out for for the test. So this just shows the shape of the training, and then you can also modify this to see that the shape of the test as well. You would notice that 70% goes to training, and then 30% goes into the shape. Now we'll now try to standardize the data that we have, that has been loaded into the training data set. So like I mentioned, most times when there is some form of imbalance in data sets, you would want to standardize the data set, so to reduce um, 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 misleading patterns. So here we're using the standard scalar method here, and typically it's once you fit it into the trained data set, you would have this data set, the training data set, standardized, and then you can also use that same scalar to transform the test data set. And then here we have the mean and the standard deviation. The idea is to, as much as possible, have the standard deviation as close to 1 as possible, so that it's well balanced. The data set is well balanced. So we've done that, and then in building the baseline model, we'll be using dummy classifier in scikit-learn. The dummy classifier is a simple and interpretable baseline model. It's a baseline model that helps perform comparison. Excuse me. It helps it provides a performance benchmark for more advanced models. So the dummy classifier helps create a model that can then be used in comparing more advanced models that have been fine-tuned and built using the same data set. So it is particularly useful in scenarios where simplicity and interpretability are valued, or when assessing the effectiveness. So for our dummy classifier today, we'll be using the most frequent strategies. So there are different strategies which are listed here. We have the uniform strategy, we have stratified, we have prior, we have most frequent, and then we have constant. So for this session, we're focusing on using the most frequent, and we're also using the stratified. So you can, at your spare time, check out the other ones, just to get a sense of how this works as well. So for the strategy, for the most frequent strategy, it predicts the most frequent class in the training data. So it prints the most frequent class that we have in the training data. That means it ignores all the input features and simply predicts the class that occurs most frequently in the training data. So we can run that quickly using specifying the strategy here. This is using most frequent, and then we would also use we would also use the stratified. Now here is the stratified, and we have the prediction here. So what we have done here is to I used two strategies. I'd use the most frequent, and then I also use the stratified. So what it has tried to do is to one, fit the model, the dummy classifier, into the trained data. Now remember that the trained data has been scaled, so that's why you have the scaled data here. And then so once it's done the fit, you can then use that same um, that same model to predict the test data, the scale test data, and that's what we have done here. And we have our prediction. So in this case, we have predictions, and then recall that what we have used to make these predictions are our test data, X tests. Haven't scaled it. Now it implies that we have predictions of what for the target values, and then we also have the the values, the targets in our data set, because this came with the ones that came directly with the data set. So we can use, do a comparison of those two to check out the performance of this baseline model itself, before we go on. So that's what we have done here to do a comparison. So we have the actual, which is part of our y our test y values, and then we also have the predicted. So here it shows it shows the predicted and then the actual, and then here you can see some are similar, and then some there are they differ here. So we can again do some evaluation of this baseline model using accuracy score and confusion matrix. So here you can see that, yeah, our baseline model, at some point, predicted accurately, and then at some other point, also, gave the wrong prediction. But then all that can be, further validated through the accuracy score and the confusion matrix. So we're going to calculate the accuracy score. It's also a function that we have loaded into the notebook. And then we also have the confusion matrix here, and both of them would help quantify the performance of the baseline model itself. So once we have that in there, we do a run, and it shows us the accuracy. Here, this shows us the accuracy score. So this shows that our baseline model is 48% accurate in terms of the prediction. And then the matrix here gives an overview of of the true positives, false negatives, false positives, and all. It helps show in true the true color of the baseline model. There are different, these are different quadrants, and this shows that negative, that's true negatives, and then this shows that negative, and then the positive, this is false positives. And from there we see that it provides the count of true positives, false positives, true negatives, and false negatives for the predictions. And based on these figures, you can do some further calculation on the precision, on the recall, and the F1 score. If you want to, you can go into further metrics that show the performance of the model. But then it just helps to show that we have 136 occurrences of the false positives. We have 159 occurrences. We have 153 occurrences of negative, false positives. This is false positives. 153 occurrences of false positives. 156 occurrences um, of true positives. We have 136 occurrences of false negatives, and we have 159 occurrences of true negatives. So it's that matrix just gives an overview, and then like I said, you can go into um, further analysis of the precision, the recall, the F1 score, as required, just to show what the baseline model, the baseline model's performance. And we can quickly have that here. Here it shows that the precision is 0.50, that's 50%, and then the recall is 49%, and then also the F1 score. So in conclusion, really, our baseline model has a precision score of 0.51, which indicates that the model has a high rate of false positives, which means that it is incorrectly classifying many observations in class 0 as class 1. And then we have the recall score of 0.5, which indicates that the model has a balanced rate of false negatives. But again, it's still, the false negatives are on the high side. So all this, shows, the performance of the baseline model. But again, like we had said, the baseline model is just to have a basis for comparison, so that when a model is built and used in prediction, you can have a benchmark. So just like we have the precision here and we have the recall score here, any other model that is built, or whatever advancement is done, or whatever advanced model is built from this data, can actually be validated and compared to the figures that this model has given us, and then that can be used to make a decision as to whether the model is performing accurately or performing as expected, or whether some fine tuning, some needs to be done at some point or somewhere along the line. So that's the conclusion of the of the of this model that's been built, the dummy classifier model, and more can still be done to improve the performance, and and then use as a benchmark for subsequent models that will be built. So that would be the end of the lab work. If you have questions, or you have you can put them in the Q&A box, or you could also go to the Slack channel and drop in your questions there, and we will get to them as soon as we can.
We have one question about fitting in the Q&A. They're asking, is fitting a simple logistic regression or baseline? And I think fitting is more related to modeling and not a term of a specific algorithm or a baseline model. Fitting is used to describe how well the model suits the data. And if anyone, you can jump in there and help me. Bisi, go ahead if you'd like. Anyone else can back that up.
Yeah. I agree with you, Lindsay. Fitting is, it's more about, it's not a baseline. It's more about trying to maneuver, or it's more about trying to 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 based on a data set that has been available, you're trying to put a model to fit into that model, into that data set that has been built. It's not a baseline. It's not baseline. Typically is you're trying to put a standard. You're trying to set a particular level, a particular value that can be used for comparison. But fitting is putting in putting it into the context of the data that you have, putting a model into the context of the data that is available at that point in time.